Hello! In this video, we are going to prove the following theorem. Let a be a non-zero real number. Then for all integers m and n, a to the power of m to the power of n is equal to a to the power of m times n. Now let's first remind ourselves of our definition of integer exponents. So first, here's our definition of non-negative integer exponents. Let a be a real number. Then for each non-negative integer n, we define a to the power of n to be a real number, recursively as follows. A to the power of 0 is going to be equal to 1, and a to the power of n plus 1 will be equal to a to the power of n times a for every non-negative integer n. So for each real number a and each non-negative integer n, we define a to the power of n to be a real number. Now another thing is we have defined negative integer exponents, and we did so that for each non-zero real number a and each negative integer n, a to the power of n is a real number. I'm not going to restate what the definition of negative integer exponents are. All that's going to be important is the properties that we've proven about integer exponents in order to prove this theorem. So putting these two together, for each non-zero real number a and each integer n, a to the power of n is a real number. So now let's remind ourselves of some of the results that we have proven. Our first result is, let a be any real number. Then, for all non-negative integers m and n, a to the power of m to the power of n is equal to a to the power of m times n. Second, let a and b be non-zero real numbers. Then for all integers n, ab to the power of n is equal to a to the power of n times b to the power of n. For all integers n, 1 to the power of n is equal to 1. Let a be a non-zero real number. Then for all integers m and n, a to the power of m times a to the power of n is equal to a to the power of m plus n. And finally, let a be a non-zero real number. Then for all integers n, a to the power of n is non-zero. So, because of this final preliminary result, we're able to make sense out of both the left-hand and right-hand side of this equation. They're actually both real numbers due to this result, right? Since a is non-zero and m is an integer, it follows from our final result that a to the power of m is a non-zero real number. Because a to the power of m is non-zero and n is an integer, we know that when we raise a to the power of m to the power of n, it will be a real number. So we're good there. And also, since a is non-zero and m times n is an integer, we know that when we perform a to the power of m times n, it'll be a real number. Okay, so now let's get into proving this theorem. To start out the proof, before we get into proving this statement, we're first going to prove some preliminaries. Working with arbitrary integers m and n, well, notice if we multiply a to the power of mn times a to the power of negative mn, according to our fourth preliminary result, we can add the exponents. This is going to be a to the power of mn plus negative mn. Adding the exponents, this is a to the power of 0, and we know any real number to the power of 0 is 1. So, when we multiply these two guys together, we get 1. Another thing is, if we multiply these guys together, a to the power of m to the power of n times a to the power of m to the power of negative n, we know that a to the power of m is non-zero. So then, applying our fourth preliminary result, we can add the exponents n into negative n. So this is just a to the power of m to the power of n plus negative n, which is just a to the power of m to the power of 0. But then any real number to the power of 0 is equal to 1. So that gives us 1 as well. And finally, if we perform a to the power of m to the power of n times a to the power of negative m to the power of n, well, what happens when we multiply these guys together? Well, according to our final preliminary result, a to the power of m and a to the power of negative m are non-zero real numbers. So then by our second preliminary result, we can multiply them, and that is all raised to the power of n. But then applying our fourth preliminary result, when we do a to the power of m times a to the power of negative m, we can add those exponents, m plus negative m. That gives us a to the power of 0 to the power of n. But any real number to the power of 0 is 1. So this is just 1 to the power of n. And by our third preliminary result, that's just equal to 1. So what we've shown here is, given any two integers m and n, when we multiply these guys together, we get 1. When we multiply these guys together, we get 1. And when we multiply these guys together, we get 1. So now let's get into proving the statement we're trying to prove. Now to prove this, we are actually going to prove 4 separate statements. We're going to first prove if m and n are any two non-negative integers, then this equality holds. Then we're going to prove if m is a non-negative integer and n is a negative integer, then this equality holds. And then if m is a negative integer and n is a non-negative integer, then this equality holds. And finally, if m and n are both negative integers, then this equality holds. Let's start with our first combination. We will let m and n be arbitrary non-negative integers. Well then, by our first preliminary result, we immediately have this equality. Okay, since a is a real number, m and n are non-negative integers, this equality holds automatically by our first preliminary result. So now let's move on to our second combination. Let's give ourselves an arbitrary non-negative integer m and an arbitrary negative integer n. Now the idea is we perform a to the power of m to the power of n times a to the power of negative mn. But then we can rewrite this second factor as the following. We could write it as a to the power of m to the power of negative n. The reason why is because we know m and negative n are both non-negative integers. So by our first preliminary result, we are able to multiply the exponents here. Well, when we multiply the exponents, this is just a to the power of m times negative n, which is a to the power of negative mn, right? So that's just equal to that by our first preliminary result. But what happens when we multiply these guys together? According to what we showed right here, we multiply them together, we just get 1. So this is just equal to 1. We also know if we multiply these guys together, we're going to get 1. So what we've shown here is the product of these two guys is equal to the product of these two guys. But remember, a to the power of negative mn is a non-zero real number by our final preliminary result. So by the cancellation law, we get a to the power of m to the power of n is equal to a to the power of mn. And that's it. So now let's move on to our third combination. We will give ourselves an arbitrary negative integer m and an arbitrary non-negative integer n. The idea for this case is, again, we're going to do exactly the same thing that we did in the second case. We're going to be performing a to the power of m to the power of n times a to the power of negative mn. Now, we're going to express this second factor in a different way. Now instead, we could write that it's the same thing as a to the power of negative m to the power of n. So these two guys are equal. The reason why is due to our first preliminary result. Notice, negative m and n are both non-negative integers. So by our first preliminary result, observing what we have here, we can multiply the exponents. So when we multiply the exponents, that's a to the power of negative m times n, or we could just write that as a to the power of negative mn. Right, so this guy is equal to this guy. But then, according to what we established above, what happens when we multiply these guys together? Well, notice, when we multiply them together, we just get 1. So this is just equal to 1, but when we multiply these guys together, we get 1. So we have a to the power of mn times a to the power of negative mn. Remember, a to the power of negative mn is non-zero. So by the cancellation law, we get a to the power of m to the power of n is equal to a to the power of mn. And that's it. So now we have one more combination left. We will suppose m and n are both negative integers. Now, to demonstrate that this equality is true, we are going to be using our third combination, right? We have proven if m is any negative integer and n is any non-negative integer, then this equality is true. So in particular, taking m to be the m we have here, and taking n to be negative n, right? Remember, in this case, the n we are working with is a negative integer. So negative n is a non-negative integer. So we'll take n to be negative n that we have here. So negative n. So in that case, what does this become? We have a to the power of m to the power of negative n is equal to a to the power of m times negative n. Or we could just write that as a to the power of negative mn, right? That's the same thing as that. So really, these guys are equal. So we're applying 3. We're going to be multiplying these two guys once again. But the idea is, we know by 3, this guy is equal to this guy. But then what happens when we multiply these two guys? According to what we established above, when we multiply them together, we just get 1. So that's equal to 1. But we know that when we multiply these guys together, we get 1 as well. So now we see that the product of these two guys is equal to the product of these two guys. Again, a to the power of negative mn is non-zero. So by the cancellation law, we get a to the power of m to the power of n equals a to the power of mn. And that completes our final combination. So given any two integers m and n, one of these 4 cases happens. No matter which case we have, we see that, well, this equality is true. So this completes the proof. And so yeah, that's pretty much it for this video.